Hello everybody, my name is Schneider. This is my MT1000 electrocardiogram. Your very basic EKG monitor, or heart monitor. Before we go into the design and implementation of the device, let's talk real quickly about what an EKG signal is. An EKG is the voltage your heart produces when it pumps blood in and out of the four chambers. And those squiggly lines is what's called the EKG or electrocardiogram. And that signal is really small. It's really small. It's typically between 0.5 and 5 millivolts. And so you have this very small signal that's buried under all these other signals coming off the body. Because you have other organs producing signals, and as well as your body's picking up signals from your atmosphere, your wall, your cell phone, light actually affects your system, not your body, but it affects your system. So you have all these noise just in and around the system, and you're trying to just get this very small and very particular type of signal called the EKG. Some of the techniques that we use to isolate the EKG is limiting the type of noise coming from components. So for instance, if you use surface mount components versus these through holes, that would help limit the type of noise coming off each of these components. But surface mount have less noise associated with them than that of through hole. Other techniques you can use is what's called a right leg drive. A right leg drive would take the common mode noise from your body, invert it, and then send it back to the body. Right leg drive. You're driving the body at the inverted noise that's coming off the body, and that would help cancel the two out. The incoming and outcoming would cancel, and you'd get a cleaner signal that way. Other ways you can do, such as I'm doing right now, is using a battery power system, so the system's isolated from the wall. You can use also shielding. So you can actually use all those techniques to help get a very clean signal. Let's go into the design now, or the implementation. We have our instrumentational op amp. It gets differentiated through here, and it goes into an integrator circuit, and the integrator helps smooth out the output by averaging the output over time, and it gets rid of what's called baseline wandering. Because baseline wandering occurs from the slower signals that the body produces, such as your breathing, that would cause your EKG signal to wander up and down. If you were to watch it over time, you would see it go up and down, following your breathing patterns and others, organs that produce slow signals. So that integrator helps get rid of that. After that, we go to a second order active filter, which in my case acts as both a anti-aliasing filter for my ADC and further getting rid of noise from 60 Hz noise, because my cutoff is at 40 Hz. So it does those two things. After it goes through that, it goes into my ADC, my 10-bit ADC, and then it's processed. Right here we have an 8-bit fixed point processor. This is a bad idea. Please do not do this. This is something I promise you I'll never do again. If you're doing floating point operations, you want a floating point processor, especially for what I'm having to do here. For this particular device or this particular implementation, I needed a 101 tap FIR filter. Now with IRs you can get lower numbers, but even this thing didn't like IRs either. But just doing those floating point operations, you want to have a floating point processor, because this thing has to write to the LCD, do the filtering, send a signal out to the piezo for a sound, and it was getting bogged down really quickly trying to do all that. And so floating point, a stronger processor with floating point, you can't go wrong. Another issue I've had again was with this LCD. The two issues I had with the LCD. Number one issue I had was matching baud rate. By far the biggest issue I still have. Even in this demonstration, you might even see it. If your baud rate does not match, you're sending artifacts, it'll mismatching commands, it'll flicker the screen, it'll cut it off, it'll do all kind of crazy stuff. So getting a very precise matching baud rate would be the best thing you can do when talking to the LCD. Next thing I had with the LCD was I had chosen serial interface, and that serial interface, even though it's 115K baud, it was still too slow to do everything I wanted to do. So I had to basically reduce how much I want to put on the screen, because that just wasn't fast enough. And so if you can get it faster and you will still use serial, great, wonderful. But at 115K, I was having issues doing a lot of things with it. So I would assume you might have the same kind of issues, at least with this type of interfacing. Besides that, let's just quickly go over so yeah, I did 101 FIR filter to get the signal, to get a low pass. I did 101 FIR low pass filter, and then I did I think a 50. I did another IR or FIR filter to isolate the QRS complex, which is what I used to do my peak detection, to do my heart rate. So I would do a peak detection for that QRS, and every time it occurred, I would mark it, have a timestamp associated with it, and then I would use the time difference to tell me my heart rate. And as well, its occurrence would then tell my processor to, hey, send out a sound through the piezo. So that's what that's doing. But again, like I told you, the fixed point processor did not like doing all that stuff, so it took me a really long time trying to tweak it and mess with it to where it would behave and be fast enough to where you can see it on the screen. Besides that, let me just show you how this thing works real quickly. Let me pause and see if I can set it up. Alright, here we go. So now we're going to turn the system on. Alright, it says a greeting in Japanese, and it says place your left finger first, relax, and then the right finger I'll place after that. The reason it says left and right is with this particular differential amplifier, for it to bias correctly, you have to connect the not inverting side. No, you have to connect the inverting side first before you connect the not inverting side. This is the INA 122, 122P, 122, and that's how it works. You can look at the data sheet if you want more specifics on that particular device, that IC chip. So here I am. I'm going to try to see if I can stay real steady. Grab the left one first. And then grab the right. I'm not hearing any sound because my piezo fell off, so let me see if I can get that piezo back on. 1 second. Okay, let's try this again. Hold this really steady, and there you have it, my EKG. I was hoping it would show some of the artifacts that occur due to mismatching baud rates, but for whatever reason it's behaving right now, which is, I guess, a good thing. Alright, that's enough of that. So, again, what I would suggest in terms of improving on the project would be figuring out a better way to interface through the LCD, get a perfect matching baud rate. I would also say use surface mounts, use a floating point processor versus this fixed point processor. And if you want to get cute, even have a wireless LCD. That would be real nice. That might impress the judges, having your LCD sitting somewhere and having the device on your person and then showing them your heart rate and the signal generation from a distance. That would be nice. So yeah, that's what I would suggest. Have fun with this project, and I hope you enjoy the semester.